Okay, this is question 11 from the summer 2004 paper 1 further maths exam. Part I asks us to find the acute angle between the line L, whose equation is this thing here. Another way to write that would be R is just equal to the parameter S times 221. So it goes through the origin when S is equal to 0. And the plane pi 1, whose equation is x minus z equals 0. Alright, and so obviously this line and this plane intercept at the origin and nowhere else, because if they did intercept anywhere else besides the origin, we would need to have x equal to z, which clearly doesn't happen. Alright, so the normal vector of this plane is clearly 1, 0, negative 1. And so if we're going to find the angle between them, we simply find the angle between the direction vector 2, 2, 1 of the line and the normal vector of the plane, which we can do using the dot product. So 2, 2, 1 dotted with 1, 0, negative 1 is equal to 2 times 1 is 2 minus 1 is 1. And it's also equal to the length of this vector, which is the square root of 9, which is 3, times the length of this vector, which is square root of 2, times cosine of the angle between them. And therefore we have that the angle between them is equal to cosine inverse of 1 divided by 3 square root of 2. And that's equal to 76.4 degrees to 1 decimal place. Now this isn't the final answer, you have to be a little bit careful. Let's take a look at what we just calculated. If this is our plane, which was called pi 1, then pi 1 has a normal vector like this, and then our line looks like this, and this can be the direction vector of the line. The angle that we calculated was actually this one here, theta. But we don't actually consider it to be the angle between the line and the plane. The angle between the line and the plane would be, if you imagine the sun is above, and it's casting a shadow down onto the plane, then the shadow underneath the line would look like this. So this line is inside the plane. It's the line has been projected down onto the plane. The angle that we're actually looking for is this one here, which we can call alpha. Now clearly alpha is equal to 90 minus theta. So actually the final answer is angle between line and plane is equal to alpha, which is equal to 90 minus theta, which is equal to 13.6 degrees. So be careful with the questions about asking you to calculate the angle between a line and a plane. I suggest always drawing a little picture to make sure you get the right angle. Okay, part 2 says find in the form ax plus by plus cz equals 0 the equation of the plane pi 2, which contains L and is perpendicular to pi 1. So if it contains L, then that means it's parallel to the vector 2, 2, 1. And if it is perpendicular to pi 1, that means it must be parallel to the vector 1, 0, negative 1, because by definition this vector n was perpendicular to pi 1. Alright, so let's write down some of these details. So pi 2 is parallel to those two vectors that we discussed, 2, 2, 1 and 1, 0, negative 1. And since it contains the line L, and the line L passes through the origin, that means that pi 2 also goes through the origin. So we can say contains the origin, 0, 0, 0. And I think now it's fairly easy to find the equation of our plane. We can get a normal vector by just taking the cross product of these two vectors. So 2, 2, 1 crossed with 1, 0, negative 1. So 2 times negative 1 is negative 2. And then 1 times 1 is 1 minus negative 2 makes 3. And then 2 times 0 is 0 minus 2 makes negative 2. So therefore pi 2 has the equation negative 2x plus 3y minus 2z is equal to d. And we know that d is 0 because it goes through 0, 0, 0. Okay, moving on to part III. Find a vector equation of the line of interception of the planes pi 1 and pi 2, and hence or otherwise show that the vectors I minus k, 2i plus 2j plus k, and 3i plus 4j plus 3k are linearly independent. Oh, I'm sorry, linearly dependent, not linearly independent. So let's write down what linearly dependent means. So linearly, vectors v1, v2, vn are linearly independent if for alpha I real numbers we have alpha 1 v1 plus alpha 2 v2 plus alpha n, whoops, alpha n is not a vector, vn is the vector. So if this is equal to 0, then that's true. That implies that alpha 1, alpha 2, alpha 1 equals alpha 2 equals alpha n equals 0. So the only way you can write the sum of these vectors times constants, whatever constants you like, the only way that can equal, by the way, this is the 0 vector. The only way that can equal the 0 vector is if all these constants are equal to 0. So that would make the set v1 to vn linearly independent. Now here we have linearly dependent, so that means there are non-zero constants alpha I such that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to the 0 vector. And another way to say that is you can write one of the vectors as a sum of the other two. So v1 is equal to beta 1 let's say beta 2 v2 plus beta 3 v3, where beta 2 and beta 3 are also real numbers. So those two things are equivalent to each other. Anyway, let's go ahead and actually solve this question. So I. So we have the equation of pi 1 is x minus z is equal to 0, and we have the equation of pi 2 here. And to find the line of intersection of pi 1 and pi 2, it's pretty easy. You just need to find 2 points that satisfy both of these equations, and then those 2 points are on both of the planes, and therefore they are on the line of intersection of the planes, and therefore you can find the vector equation of that line using those 2 points. One of the 2 points is clearly x equals 0, y equals 0, z equals 0, so 0, 0, 0 is one of the 2 points. let me write it as a point first. So 0, 0, 0 is on the line. And then let's suppose that x equals 1, then z also equals 1. And if x equals 1 and z equals 1, then we have that minus 2 plus 3y, and then just minus 2 is equal to 0. And so that will mean that y is equal to 4 over 3. So another point is 1, 4 over 3, and 1. So this is also on the line. And therefore a vector equation of the line, well, if 0, 0, 0 is on the line and this point is also on the line, then clearly the line just looks like this. R is equal to t times 1, 4 over 3, 1. Or t times any multiple of this vector. For example, you can times everything by 3. So lambda is equal to t over 3. And write it as 3, 4, 3. That's fine too. And so now we want to somehow use this to show that the vectors, so 1 and 0 and negative 1. Let me just write these down. 1, 0, negative 1. 2, 2, 1, and 3, 4, 3. They are supposed to be linearly dependent. By the way, I gave you the algebraic definition of linearly dependent before. Let's quickly take a look at the geometric definition. So suppose that V3 can be written as a sum of V1 and V2. It doesn't matter which one I pick, by the way. If one of them can be written as a sum of the other two, then any one of them can be written as a sum of the other two. So let's suppose that V3 is equal to alpha 1 V1 plus alpha 2 V2. Then what that means is that if we have a plane spanned by V1 and V2, then it means that V3 is somewhere inside this plane. So I don't know, maybe this is alpha 1 times V1, and this can be alpha 2 times V2, and so that would mean that V3 is over here. And observe that this means it is contained in the two-dimensional plane that is spanned by the vectors V1 and V2. So it's made up of all the multiples of V1 and V2 added together in this form. So it's a two-dimensional plane embedded in three-dimensional space. So that's the geometric definition of linearly dependent here. So, I mean, even though we could quickly answer this question by saying, or just making the observation that 3, 4, 3 is equal to, well, negative 1 times V1, so negative 1, 0, negative 1, and then plus 2 times V2. So it's 2 times 2, 2, 1. So that proves they are linearly dependent. Let's look at the situation geometrically as well, because I think the question is kind of encouraging us by the whole and hence part to use the information that we've collected so far. So let's write down what we know so far. So let's suppose that this is our plane pi 1. And we have that pi 2 contains L and is perpendicular to pi 1. So this can be pi 2. It meets pi 1 at right angles there. So this is orthogonal. So pi 2. and pi 2 contains it contains the line 2, 2, 1 times the scalar. So let's say r equals s times 2, 2, 1. So in other words, it's parallel to the vector 2, 2, 1. And we have also that it is parallel to the normal vector of pi 1, which is 1, 0, negative 1. And we have the direction vector of the line of interception is 3, 4, negative 3. No, sorry, 3, 4, positive 3. And from here, everything becomes pretty easy to see, because we observe that this green vector 2, 2, 1 is not parallel to this red vector 3, 4, 3. There's an angle here, theta, which I believe we figured out before was 13.6 degrees. And so from there, just observe we can move this blue vector over to here, no problem. And so we can see the green vector 2, 2, 1 is inside the plane that is spanned by the blue vector 1, 0, negative 1 and the red vector 3, 4, 3. So this green vector is contained entirely within that plane. So it's like, go and draw it like this. And so it is some multiple of the blue vector plus some multiple of the red vector. Therefore, the three vectors are linearly dependent. Now, in your exam, I would say probably just do it this way. It's way faster. Just observe that one of them is a multiple of the other two. And even if it's not obvious like that, you could just write 3, 4, 3 is equal to x times 1, 0, negative 1 plus y times 2, 2, 1, and then just find what x and y are. But since we're learning here, it's fun to take a look at the geometric approach, and it's gives you a more intuitive explanation of what's really going on. Okay, and lastly, part IV. The variable line M passes through the point with position vector 4, 4, 2 and is perpendicular to L. The line M meets pi 1 at Q. Find the minimum distance of Q from the origin as M varies, giving your answer correct to 3 significant figures. So for this one, I guess you have to do a little bit of visualization here. So we got this variable line M. Okay, so its variable means it can be any line which meets the conditions of going through the point 4, 4, 2 and being perpendicular to the line L. So we can also make the observation that the line L itself also goes through the point 4, 4, 2 when S is equal to 2 there. Let's draw a little sketch. Okay, so we've got our line L. Okay, here's the origin O. And let's say this is the point 4, 4, 2. Then actually the line M can be any line that looks like this. So it can be this line here. It can be this line here. It can be this line here. And if you really think about it, it's going to create an entire plane. And again, it goes on forever in all directions. But every single line inside this plane is perpendicular to the line L. But any point inside this plane, for example this point here, it's going to be on one of these lines that is perpendicular to the line L and also goes through the point 4, 4, 2. And any point that is outside the plane is either on a line that is not perpendicular to L, or it does not go through the point 4, 4, 2. So this plane, which we can call pi m, contains all of the possible points along one of the variable lines M. And we know that L had the direction vector 442 or 221 or whatever. Doesn't matter. And so we know that the equation of pi m is going to be 2x plus 2y plus z is equal to d. And we also know that the point 442 is on the plane, so that gives us that d is equal to 2 times 4 plus 2 times 4 plus 2, which would be 18. Alright, and from there, we are told that the line M, which could be any of those points in that plane, meets the plane pi 1 at Q. So pi 1 is this plane here. So the plane pi 1 has equation x minus z is equal to 0. And these two intercept at the point Q. Well, we can find the equation of the line of interception between these two planes here, just by finding 2 points of interception. So the first point of interception, the first point is when we can take x and z equals 0, and then so 2y equals 18, so 0, 9, 0. And then another point, we can take x and z are equal to 2, just to keep things an even number. So 2 times 2 is 4, plus 2 is 6. So that would make 2y equal to 12, so y would be equal to 6. So 2 is 6, 2. So let's say this is the vector OA and the vector OB. Okay, so the line of interception is OA plus t times AB. So that would be 0, 9, 0 plus t times OB minus OA. So 2, negative 3, 2. So these are all the possible values of Q. These are all of the points where any one of these lines M could intercept the plane pi 1. And then the question was just asking us to find the minimum distance of Q from the origin as M varies. So in other words, find the smallest distance of all these points from the origin. So let's go ahead and sketch that. So we got our origin O, and then we got our line, and here's the point 0, 9, 0. And then this is the vector 2, negative 3, 2. Okay, and we're looking for this point x. Because that will be the minimum distance. So this is 90 degrees. So we know that OX is on this line, so it's equal to, well, 2 times x plus, and then the next coordinate is 9 minus 3x, and the last coordinate is 2x again. Okay, so it takes this form here, but we also have OX dotted with 2, negative 3, 2 is equal to 0. OX dotted with 2, negative 3, 2 is equal to 0, and it's also equal to 2x times 2, so 4x minus 3 times 9 minus 3x, and then plus 2 times 2x, so plus 4x. Okay, so we got 8x minus 27, oops, not 29, 27 plus 9x. So we get 17x equals 27. And so x is equal to 27 divided by 17. And so we can write our vector OX is equal to 2 times 27 over 17. So that'll be 54 over 17. And then the next coordinate is 9 minus 3 times 27 over 17. Which is 72 over 17. And then the last coordinate is just 54 over 17 again. And we just need to find the length of this vector. So clearly that's going to be 1 over 17 times the square root of 54 squared plus 72 squared plus 54 squared. And that gives us 18 times the square root of 34 divided by 17. And we were supposed to give the answer to 3 significant figures. So that is equal to 6.17 to 3 significant figures. And so we're done with this question. Long question, actually.